So let me just briefly remind you what happened yesterday. You know, it's like you watch miniseries. In the beginning, there's a recap. So, introduced this basic signal recovery problem. You send a signal via its Fourier transform. Some of the frequencies are lost. And the question is, under what reasonable or unreasonable conditions can you recover the signal exactly and uniquely? Okay, so we talked about how the uncertainty principle plays a role. And then we discussed the fact that the uncertainty principle in its traditional form is very seldom sharp. And proved a variety of results that say that in the presence of any non-trivial Fourier restriction estimate, one gets a better restriction estimate. Okay? One of the uncertainty principle that was stated was the so-called energy uncertainty principle, and I'm going to state it again. And this one tells you directly and explicitly that if the additive energy of your set is better than the trivial, then you get a better uncertainty principle. Okay, and so here, just as a quick review, this is what it means for a set S to satisfy a PQ restriction estimate. So the normalized LQ norm of the Fourier transform restricted to the set S. I just noticed that I'm talking too fast again. I'm going to slow down. I'm going to relax. I just had a very nice lunch. I should have had a beer. Okay, so the normalized LQ norm is bounded by a constant, and we should always think of this constant as being some bounded number, and capital N should be at least as large as the number of administrators at a typical American university. Okay, and maybe infinity should not be mentioned, but anyway, and so it's n to the minus d over 2 times the non-normalized LP norm of F, and just if you're not used to working with these objects, so you see that this normalization is reasonable because if you just apply the triangle inequality to the left-hand side, you get the right-hand side with p equals 1, which not only suggests that this normalization is reasonable, it also says that the restriction estimate always holds when p equals 1. Okay, and okay, yeah, it just takes a minute to go. And this is the so-called universal restriction estimate that I mentioned at the end of the other talk. And it's universal in the sense that the geometric information is not buried into the constant. It is written out explicitly, which means that this estimate always holds. If it always holds, doesn't mean that it's always useful, but it always holds depending on the size of S and the additive combinatorial properties encoded by this quantity energy divided by the size of U squared, max over the subsets. Okay, so this is roughly the recap of what happened yesterday, and my talk. Okay.
So, but this way you can only get P, which is 4/3.
Yes, this way you can get 4/3, but also, I certainly do not mean to suggest that this is the only universal restriction theorem one can prove. It's just that this one lends itself to a fairly simple proof, which I'm able to present within time constraints. So you can write a variety of statements of this type. In fact, you're going to see some today. Okay, so something always doesn't quite work. I will just use this one. It's okay. It's okay. Life is good. All right. So also another thing that I started doing at the end of the talk that I'll briefly review just to sort of get into this material for today more smoothly is how to use the restriction theorem directly and in a very simple and direct way. This doesn't give you the best exponents, but it does show you a clear improvement in the case when you have a non-trivial restriction estimate. I will give you more efficient mechanism a bit later today. Okay, so this is joint work with Zita Miami from last year. So F and F hat are signals. F is supported in E, and the Fourier transform is supported in S. And suppose that S satisfies the PQ restriction estimate with norm CPQ. Then you have the following uncertainty principle. The size of E raised to the power of 1 over P times the size of S is bounded from below by n to the d over CPQ, where this is the norm. Once again, if the norm CPQ is some number like 10 and capital N is huge, then we have a gain over the classical uncertainty principle, which is afforded to us by the power 1 over p. Okay? So this, again, shows this is not the most efficient version. You're going to see better ones in a moment, or in a few moments. But it does show that you get an improvement with any non-trivial restriction theorem. I also mentioned last time that there's some potentially very interesting results around the endpoint. So if you don't get, so instead of having L1 plus epsilon restriction theorem, you can prove L log alpha L, for example, theorems, and those have interesting implications as well. Okay, so let's prove the uncertainty principle via restriction. I went over this proof in the end, but in my experience for listening talks, I typically don't remember what happened in the last 5 or 10 minutes. So let me go over this. So once again, you write a function as an inverse Fourier transform of its Fourier transform, but by assumption, you restrict the sum to S, because the Fourier transform is supported on S. Okay? We apply Hölder's inequality, and this gets us n to the minus d over 2 times the size of S times the normalized LQ norm of the restriction operator. Okay? Then by assumption, the normalized LQ norm of the restriction operator is bounded by CPQ, n to the minus d over 2, which combines with the n to the minus d over 2 we had to produce n to the minus d, times the not normalized LP norm of the function. Okay? Life is good? Okay. And by the support assumption, we can localize the LP norm to x in E. I also mentioned in passing, and I'm going to say more about this later, more precisely, but so far, I've been assuming throughout that the function is supported in the set E, and the Fourier transform is supported in the set S. These hypotheses can be replaced by concentration hypotheses, which are more likely to occur in nature. Okay. Moreover, in the Euclidean case, it's outright impossible for a function to have compact support if its Fourier transform does. It's incredibly annoying. I found this annoying my whole professional life, but that's how it is. Okay. And so if we put everything together, we see that modulus of f of x is bounded by the size of S, the norm of the restriction operator, n to the minus d, times the LP norm over the set E. Okay? And now we raise both sides to the power of p, and we sum. This introduces the size of E. Okay? And then we put n to the minus d to the other side, and this makes it n to the dp. Now we simply take the pth roots, and we recover the improvement in the uncertainty principle that I mentioned. Okay? So this completes the proof of the uncertainty principle via restriction, but I'm going to come back to this theme over and over from a variety of different perspectives. By the way, let me remind you of what I said yesterday. Please interrupt me anytime for any reason. If I cover less than I planned, it's okay. All right, so now let me prove the universal restriction theorem. Just in case you don't remember what it said, here is the universal restriction theorem. It says that the L2 norm, normalized L2 norm of the restriction operator is bounded by, so you have a ratio of the size of S to n to the d over 2 raised to the power of minus a half. And then you have a maximum over the subsets of the energy divided by the size of the set squared raised to the power of a quarter. And then n to the minus d over 2 times the L4/3 norm of f. And just to avoid this becoming a forest of symbols flashing by, the example that I recommend keeping in mind is the one that I mentioned yesterday. Namely, take n to be a large prime, take d to be 2, okay, so, and let S be a unit circle. If S is a unit circle, then this first quantity is essentially 1, not exactly, because it's n plus or minus 1, but essentially 1. And the second quantity is 3 to the power of 1/4. Because if you choose any quadruplet, x, y, x prime, and y prime on a circle, then x plus y equals x prime plus y prime if and only if x, y, and x prime, y prime are the same up to permutations, or if they're antipodal. Okay? And this is kind of a trivial, but to me an interesting point, is that in the plane, we of course naturally think of this as a trigonometric fact. It easily follows from elementary trigonometry. But actually there's no trigonometry in it. It's just an algebraic fact, which can be deduced by symbol pushing. This is why it generalizes to almost any field setting. Okay, so now let's go ahead and prove it. Okay, so as I mentioned, the proof is, even though it looks very different because there are fewer technicalities and it sort of comes at it from a slightly different point of view, but this is basically Pfefferman's proof of the two-dimensional Butner-Rees conjecture. Okay, so what do? You take the sum over m in S, f hat of m squared, and you write it as an indicator function of S times f hat of m times the function g, where g is just a complex conjugate of the first one. Okay, so why is it necessary to introduce another function? Because at some point in the past we took calculus 1 and we became very excited when integral of e to the x sine x was solved by integrating by parts twice and for solving it in terms of itself. Well, this trick is a gift that keeps on giving, as we all know, right? And so this expression equals what? We simply recycle it. We write down the Fourier transform of f, and we hit the indicator function of S times g with the Fourier transform, and we obtain summation over x, f of x, times the Fourier transform of the indicator function of S times g. Okay? Of course, what are we doing here? We are turning a restriction inequality into an extension inequality. But I really dislike throwing words around, and since everything is explicit and simple, I'm just writing it out. Okay? And so this is bounded by the L4/3 norm of f times the L4 norm of the Fourier transform, and one might have guessed that it has to come up because there is energy, there's additive energy in the solution. And how do you get at additive energy? By considering the L4 norm of the Fourier transform. Okay, so all of this goes back to when dinosaurs still walked the earth. The basic ideas. Actually, everything does. Okay. And so now we look at the L4 norm of the Fourier transform to the power of 4, and we simply expand it. Okay? And so we have n to the minus 2d from the normalization of the Fourier transform. We have 4 copies of g, and possibly for the first time in my life, I put complex conjugates in the correct places. Okay, and then you have summation of chi of m plus l minus m prime minus l prime dot x. Now we apply orthogonality, and now this is equal to n to the minus d. We lost n to the power of d from the orthogonality, and then we have 4 copies of g. And we're summing over m plus l equals m prime plus l prime. Is everything cool?
You're missing a left parenthesis.
I'm missing a left
parenthesis.
where?
So the
Oh my God! Yes, I do. Yes, I do. This is slide number 35. Up here. We'll remember this. Okay. Okay, and now here I took a small shortcut, but it is very simple. So if G is an indicator function of a set, then it is clear that you simply get additive energy of U and then divided by U squared. If G is not the indicator function of a set, you simply write your function as a linear combination of indicator functions, and everything comes out. It's a tedious calculation, and I just didn't think anybody would learn anything from it. So, but this clearly holds.
This is why you get the maximum?
Well, yeah, because G could be G could be an indicator function of any set, and when you write it as a linear combination, you have to consider all possible sets, and this is where the maximum comes in. Exactly. In the continuous setting, this business of proving the result for indicator functions and then extending by interpolation is actually a non-trivial issue. You often miss endpoints this way. In a discrete setting, there's nothing happening whatsoever. Okay. All right. So it follows from this that the L4 norm of the Fourier transform of the indicator function of S times G is bounded by n to the minus d over 4. We simply took the fourth root. Then we have this maximum of lambda of u over size of u squared to the power of a quarter, same thing. And then we simply get the L2 norm of G. And now we use the trick of from integral e to the x sine x, right? What we realize is that G, L2 norm of G is just the square root of the left-hand side in the original inequality, right? It's just the square root of this here. And so if we put everything together, we get that the normalized L2 norm is bounded by n to the minus d over 4, the maximum of lambda u divided by the size of u squared to the power of a quarter times the size of s to the minus a half times the L4 thirds norm of f. And now it's just a matter of rewriting it in the form that I wrote it in before. And this is, of course, a matter of taste. I should probably tell you why I write it in this form. The reason I write it in this form is because the critical case is when the size of s is equal to n to the d over 2. Because if the size of s is bigger than n to the d over 2, then by knuckle-dragging considerations, the lambda of u over the size of u squared, the maximum, cannot be bounded independently of n, because the number of pairs is greater than the whole space. Right? So the critical case is somehow the size of s is around n to the d over 2. This is why I chose to write it as a ratio raised to the power of minus a half. Does it make sense? Everybody with me? Life is good? It's a little warm in this room. Okay, so this completes the proof of the universal restriction theorem. All right. So now let's prove the additive energy uncertainty principle. Once again, let's go back and remind ourselves of what it says. Okay. So the additive energy uncertainty principle, there will be one more coming in a moment. It says that if you take the size of E, and then you multiply it by the maximum over u and s of lambda u over the size of u squared to the power of alpha, then times the size of s times the maximum over f and e, lambda of f over the size of f squared to the power of 1 minus alpha is bigger than or equal to n to the d. And the reason this is a generalization of the classical uncertainty principle is that lambda of u, the size of the additive energy, never exceeds the size of the set cubed. And if you simply plug that in, you get the classical uncertainty principle. Take alpha equals 1, as Thomas pointed out yesterday. Okay? So this is the additive energy uncertainty principle. I also mentioned that it would be nice to have a version of this principle which simply has to do with additive energy of E and S respectively, without having a quantity that depends on the subsets, because as one might guess, the quantity that depends on the subsets is very difficult to check, except in some very special cases like the circle. So this is truth in advertising remark. Okay, and we're going to have that. Let's prove this one anyways. Okay. So by the universal restriction theorem, we have this. So we simply write out the statement, except that this should be n to the minus d over 2. So I told you that it was inevitable that the old normalization is going to come in, the one I used my whole life until my coworkers threatened to kill me. Okay, not literally. Okay, so then it follows that that when you unnormalize it, you have the size of s to the 1/2. So this part is correct, this part is correct, n to the minus d is still wrong. At some point it's going to converge. Okay? So since the Fourier transform is supported in S, we can apply Plancherel and obtain this. So this is how it converges, because two mistakes canceled. This is what Plancherel looked like with the original normalization of the Fourier transform. But with the new normalization of the Fourier transform, this n to the minus d over 2 is not there. Now, there was an extra n to the minus d over 2 before, because you understand that the conclusions of theorems don't depend on the definition of the Fourier transform. Okay, so then you get this, it is bounded by this, so we apply Holder's, oh, what happened? We apply Holder's inequality, and so we obtain this, except that the size of e to the 1/4 comes out, because we bootstrap to L2, okay? And now it follows that n to the d over 4 is bounded by this maximum quantity involving additive energy, divided by the size of u squared to the power of 1/4, times the size of e to the 1/4. And we conclude that n to the d is less than or equal to the size of e times the maximum over u and s, lambda u over norm u squared. So I made two canceling errors involving the Fourier transform. I will fix it before posting this. My apologies. And exactly the same argument was f replaced by f hat. Actually, it's not even exactly the same argument. It follows by abstract nonsense. Gives us that n to the d is bounded by the size of s times the maximum of lambda of f over the size of f squared, where the maximum is taken over the subsets of E, and then we take the combination, the convex combination. Okay? Okay, so as I mentioned, it would be very convenient to work out a version of the additive energy uncertainty principle purely in terms of the additive energy of the support of the function and the support of its Fourier transform. This would be of more practical use, even if we get a weaker estimate in some situations. Okay? So this is once again joint work with Karam Aldalay, Iosevich, Jamango, Azita Mayeli, and Svetlana Peck. So F maps Z and D to complex numbers. So I think I mentioned yesterday that I've been getting strong undergraduate students involved in these research projects, and this is the result. So I'm really happy with this experiment. So then for any alpha in 0, 1, n to the d is bounded. Now they're additive energies, but they're only additive energies of the support of the function and the support of the Fourier transform. So it's lambda to the alpha over 3 of E times lambda to the 1 minus alpha over 3 of S times the size of E to the 1 minus alpha times the size of S to the alpha. So if you take alpha equals 0, right, then if you take alpha equals 0, then what do you get? You get the size of E times the lambda to the 1/3 of S. Now, lambda of S cannot exceed the size of S cubed. You take the cube root, you get the size of S, and this way you recover the classical uncertainty principle. And if you have better than trivial additive energy, you have a better uncertainty principle. And this uncertainty principle doesn't compare in any direct way to the previous one. Sometimes this one is better, sometimes the other one is better. From a practical standpoint, this one is certainly better because, of course, we have a much better shot at estimating the additive energy of two particular sets than estimating additive energies of all of its subsets. Okay? This makes sense? Life is good? let's prove this alternate version of the additive energy uncertainty principle. So once again, we write f of x as an inverse Fourier transform of its Fourier transform. So now I'm scared about normalizations of the Fourier transform. Let's see what happens. So it follows that modulus of f of x, this is a calculation we've seen numerous times, is bounded by n to the minus d over 2 times the size of s to the 3/4 times the L4 norm of the Fourier transform. So here, we go for the jugular, so to speak. We know that additive energy lives somewhere inside the L4 norm of the Fourier transform, so we just go for it and hope for the best. Well, I mean, we checked before presenting. Okay, so now the L4 norm to the 4th of the Fourier transform is what? You have m to the minus 2d, then you have a summation over m, summation over x, y, x prime, y prime, and e. Then you have the characters, chi of x plus y minus x prime minus y prime dot m, and 4 copies of f. So far, so good. And
so what happened to S and now it became E?
One second. Oh, no. S didn't become E. S became Z and D.
Right.
Because positive quantities. And E is a support of F. In other words, S is not being used in this estimate. But then afterwards, we're going to flip the roles of E and S and use it that way. Okay, so I should have mentioned that. So this is a simple but very useful trick that comes up a lot in these sort of Fourier analytic combinatorial inequalities. Is you bound the sum over S by sum over all of Z and D. Now on the surface, this looks ridiculous because you're giving up a lot. But what you gain is orthogonality. And roughly speaking, before even making any calculations, how do you know that it's worth it? You know that it's worth it is because orthogonality typically gains you the square root, right? So you go from n to the d to n to the d over 2, right? So if the size of S is bigger than n to the d over 2, then giving up the size of S for orthogonality is worth it, okay, roughly speaking. All right, so here we sum in M, we get our orthogonality, and now we have a sum over x plus y equals x prime plus y prime, but we have this 4 copies of f. So the question is what to do with these 4 copies of f? The most trivial possible thing. Dominate them by L infinity norm. Okay? So we bound this by n to the minus d, the additive energy of E, times the L infinity norm of f raised to the power of 4. So once again, the simple ideas here is to dominate the sum over S by the sum over the whole space and gain orthogonality, take out the functions f by the L infinity norm, and obtain the additive energy of E times the L infinity norm to the power of 4. By the way, I want to make a comment. I forget whose talk this was in, but there was a discussion of the fact that so when you work with on the Boolean cube, the image is real valued, not complex valued. I think you said this, right? So here we make it complex valued, but in practice, in most of the applications of this, of course, the values are real valued, because one of the applications of this that I may or may not be able to get to in the last lecture is application of single processing to time series analysis. And time series is real valued, people in industry insist. Okay, because they typically give you sort of the number of sales in a given day, and if you make it complex valued, they will object. Yes?
It's a non-relevant remark, but there is some imaginary time in physicists use in quantum field theory. So even time is not always real.
That's right, and then physicists tell us that we work on things that are abstract. Unbelievable, right? I mean, who are they to talk, right? Yeah. So we reach this point. Now there's an L infinity on the right-hand side, which means that at some point, I mean, the game is always the same here. So we need to find an L-infinity norm on the left-hand side and cancel them. This is how the game works. So if we put everything together, modulus of f of x is bounded by n to the minus d over 2, the size of s to the 3/4, n to the minus d over 4, the additive energy of e to the power of 1/4 times the L-infinity norm of f on e. So now we just take a maximum over x and e, we cancel the L-infinity norms, and we get this inequality, n to the 3d over 4, bounded by additive energy of E raised to the power of 1/4 times the size of S raised to the power of 3/4. And raising both sides to the power of 4/3, we get n to the d is bounded by additive energy of E raised to the power of 1/3 times the size of S. And once again, by symmetry, we reverse the roles of E and S, and we get the same inequalities with S and E reversed, and then we take a convex combination. And this completes the proof. Does this make sense? So a theme that's going to arise sort of over and over is that these constants matter. So you're going to see a couple of mechanisms that are in some ways more efficient than this, but where constants are difficult to compute. This is why sort of in the signal processing, in the area of signal processing, quite often it is worthwhile to work out weaker inequalities with explicit constants. Okay, so I always welcome an excuse to present my favorite result in mathematics. Okay, and if I had to name only one, it would be this, and this is Bourgain's lambda Q theorem. And so Bourgain proved the following innocent-looking result. The proof is anything other than innocent. So he proved that G is a locally compact abelian group, and you take any n orthogonal functions, okay, with L-infinity norm bounded by 1. Okay? Later in these lectures, I'm going to discuss a similar problem on compact Riemannian manifolds without a boundary, where this obnoxious situation arises where eigenfunctions are not bounded. Basically, what I'm about to say is an exaggeration, but basically the only time they are bounded is on a torus. Okay, I mean, there are other similar manifolds. And that makes that problem much more complicated. But for now, we're in locally compact abelian groups. We have n orthogonal functions. L-infinity norms of these functions is bounded about by 1. Then for a generic set S in 1 through n, okay, so randomly chosen set, of size approximately n to the 2 over q, q larger than 2, you take the LQ norm of the Fourier series with respect to the phis, and it's bounded by C of q times the L2 norm, just the sum of the Fourier coefficient squared, where C of q depends only on q. Okay, so in the original form, so lambda q sets, if I remember correctly, were introduced by Rudin, and there the idea was you took a trigonometric polynomial, let's say just on a torus, with frequencies in a set S, and you called it a lambda q set if the LQ norm of the polynomial was bounded by a constant that depended only on q times the L2 norm of the polynomial. Okay? And so Rudin proved, it's a very beautiful and elegant argument, that the size of S is asymptotically. So here we're in the infinite setting, S is a subset of Z, okay, because the basis is e to the 2 pi I x k, where k's are integers. So he proved that the size of S intersected with, let's say, interval from minus r to r is at most r to the power of, if you're in dimension d, 2d over q, okay? But the question became, for every q, can you construct a set that's a lambda q set, but is not a lambda p set for any smaller p? And Rudin was able to do this for even integers using the additive energy considerations. But then the question that stood for a long time is whether this can be done for any Q. And this was accomplished by Bourgain in this theorem.
So what do you mean by generic, like with high probability?
Yeah, overwhelming probability, it's exponential tails. And like I was about to say that I could write down exactly what the right estimates and probability are. This is actually not so easy to deduce from the way Bourgain writes things, but I currently have two students who are cursing my name as we speak, who were asked to write these estimates explicitly.
So this theorem, it says that you have this Q versus 2 estimate. It doesn't say that it will not work for P less than Q.
Well, it does if you combine it with the fact that the size of S cannot be larger than this.
Yeah.
Right. So if you combine these two in the case of a torus, then you get Rudin's conjecture.
I see.
Okay, so what I'm going to do now is give you an extremely simple argument that shows that any estimate of this type has a built-in uncertainty principle. Very simple, but very powerful uncertainty principle. Okay? So first of all, what is the consequence of Bourgain's lambda Q theorem? For some reason I called it lambda P. I called it lambda P because Bourgain calls it lambda P, and I forgot that I switched to Q. My apologies. No matter how many times I go over these notes, the errors don't converge. Did you ever notice that? Okay, so a consequence of Bourgain's celebrated lambda Q theorem in the case of Z and D is that if F maps Z and D to complex numbers and the Fourier transform is supported in S, then for a generic set of size n to the 2D over Q, the normalized LQ norm of F is bounded by a constant that depends only on Q, so it's independent of n, times the normalized L2 norm. Okay, just an immediate consequence of Bourgain's. We simply specialize Bourgain's theorem to the setting of Z and D. And what I'm going to do now is I'm going to show you a very simple calculation that shows that this inequality has a built-in uncertainty principle. Okay? So in fact, we're going to see that anytime you have a non-trivial estimate of this type, by non-trivial I mean that Q is greater than 2, then the support of F must be a positive proportion of Z and D. Okay? Of course, intuitively, there's nothing new under the sun. All of this has come up in restriction theory before. Here, it's simply being codified in the context of Z and D. Okay?
So the statement is that for a generic S, every F such that F hat is supported satisfied. So,
Yes.
So the quantifiers are not okay.
Yeah, so yeah, absolutely. So if you suppose you have a function which is supported in the generic set of size n to the d minus epsilon. And this epsilon can be turned into logs. I'm going to discuss that later in the lectures. But n to the d minus epsilon. Then F has to be supported in a positive proportion of the whole space. So yesterday we discussed a typical sharpness example for the uncertainty principle. And that is when you take a k-dimensional subspace, then the Fourier transform is essentially the orthogonal subspace. So you have an example of a function that is supported in a small set, and its Fourier transform is supported in a small set. Okay? So what I'm telling you is that nonsense like this doesn't take place if the Fourier transform is supported in a generic set.
Okay. So here we think of n as big.
Everything is what?
Here we think of n as large.
Well, there are constants involved, which means that it becomes more meaningful.
If I take n equals to 2, do I still get this?
No, you get this, but the constants overwhelm the meaning of this inequality. So n really does have to be the size of the American national debt. Yes. Well, I mean, no, I'm sorry. Let me give you a slightly better answer. So I did some numerical experiments with this. When n is like 1,000, these results are meaningful, but not when n is like 100. So, because the issue is estimates on Bourgain's constants. Nobody knows what they are. These same students who are cursing my name, they're also trying to estimate the constants from Bourgain's proof. I tried to estimate them numerically, and based on this, tried to understand for what range of n is meaningful. And when n is like 1,000, this is already meaningful. I can be a bit more precise than that.
But you think of D as small.
Huh?
But you think of D as being small.
Yes. Because when both n and d grow, it's a very subtle question, as we know from.
No, for us it's exactly the opposite. N is small and D is big.
That's right. That's right. Yeah, here it's a better one. All right, so let's go ahead and prove this. As I promised, the proof is straightforward. So suppose that f is supported on E and Z and D, and the Fourier transform is supported in S. So what does Bourgain's theorem imply? So we take Bourgain's theorem, we insert x in E, because we're assuming that f is supported there. We multiply and divide by the size of E, which brings out the size of E to the 1 over Q. And it also brings out n to the minus d over Q. We do the same thing on the right-hand side, where in this case, we bring out the size of E to the 1/2 and n to the minus d over 2. Okay? So now what is the idea? The idea is that we are going to put all the e's on one side, we're going to put all the n's on the other side and hope that it works out. And it works out because math works. Okay? So if we, so once again, we renormalize. The idea is to renormalize from the probability measure in the whole space to the probability measure in the set E. Okay, so it's a fairly typical trick. And now, if we put all the e's on one side and n's on the other and take the root, we get that the size of E is bounded from below by n to the d times Bourgain's constant raised to the power of 1 over 1/2 minus 1 over q. And what is being buried under the rug here is that you also get a ratio of the normalized LQ norm of F and the normalized L2 norm of F. But by Holder's inequality, LQ norm is bigger than or equal to the L2 norm, so we can simply exclude it. And what we get is this inequality. So once again, not only for a generic set, because there are sets that are quite deterministic, like spheres, for which you have a nice estimate. For any set for which you have a non-trivial restriction estimate, okay, because Bourgain's result is simply dual to a restriction estimate. Right? It's simply an estimate on the extension operator. Because you take a function that's supported on S, you extend it, and then you compute the LQ norm. So it's simply the dual operator. Okay? So in the presence of any non-trivial restriction estimate, if the Fourier transform is in the presence of any non-trivial restriction estimate, the function has to be supported on the positive proportion of the whole space. Okay? So this is what we just saw. Does this make sense? Does everything connect? Okay. And so as I said, so if f hat is supported in a generic set of size n to the d minus epsilon, then f is supported on the positive proportion of z and d. And there's work in progress now. So because what one would really like to do is to get a result not just for generic sets of size n to the d minus epsilon, but sets of the size n to the d, let's say, over log n. And if the set is random, then this is covered by a celebrated result of Kundus, Romberg, and Tell. But the whole point here is to unify the deterministic and random examples. And one would be able to do that if one could prove a version of Bourgain's estimate but near L2. So on spaces like L2 log L. And sharp estimates are not available, but there is an estimate that is non-trivial in that direction, fairly recent one about a year ago by Kashin and Limonova, and we're in the process of converting that result into the signal processing context. All right, so if we send the Fourier transform, so a summary of applications to the signal processing. So if we send the Fourier transform of a signal f supported in a set of size little o of n to the d, and the frequencies in S satisfying a lambda q bigger than 2 theorem inequality, if those frequencies are missing, then we can recover f exactly and uniquely with very high probability. In fact, as you saw, little o of n to the d is too strong a statement. It's really quite quantitative. Okay? And as I mentioned, this is, in a matter of weeks, there will be a version of this where n to the d minus epsilon is replaced by n to the d divided by a suitable power of a logarithm. Okay? And what this will do is unify approaches that are built solely for random sets with approaches that work for deterministic sets. Right? So this is the usual issue of random versus pseudo-random. Right? So there are restriction theorems. So roughly speaking, if you choose a random set, then a restriction theorem holds. This is what Bourgain proved. But also there are many deterministic objects, like paraboloid spheres, etc., for which restriction estimates are known. And one of the things that Azita Mayeli and I are seeking to unify is we're seeking to unify these two theories.
So you want to understand one quantity controls this behavior? Like this?
Yes. Basically, we want to prove uncertainty principles coming from restriction theory where you wouldn't require different methods to handle deterministic and random sets. Okay, sort of bridging the gap between random and pseudo-random in that setting. And this is certainly not the first time in mathematics where such approaches were attempted. All right, so the next topic that I would like to discuss is another point of view on the uncertainty principle from the standpoint of what are called annihilating pairs. It's a very ominous sounding title. Okay, so Safed and Nazarov in '93 proved a very beautiful inequality which has since then been generalized to death. And the inequality says the following, that, okay, I stated it in RD. Fedya proved it in one variable, but I know Fedya, he could have proved it in RD if he wanted to. Okay, so E and S in RD have finite measure. Then there exists a constant C bigger than 0, such that the L2 norm of the function is bounded by e to the power of little c times the measure of e times the measure of s times the L2 norm of the function f outside of e plus the L2 norm of the Fourier transform outside of s. Okay? I'm going to say much more about the continuous theory later in these lectures, but now let me go ahead and jump straight back into the discrete setting. Okay. So this is an inequality, and I think it's quite clear what this has to do with the uncertainty principle, right?
Mm-hmm.
And okay, so Gober and Germain proved the following result in the discrete setting. Suppose that f is a signal from Z and D to complex numbers. So they proved that if E and S are subsets of Z and D, so that the size of E times the size of S is less than n to the D, so the opposite condition from the uncertainty principle, then the L2 norm of the function is bounded by a constant, which is very explicit. It's 1 plus 1 over 1 minus the square root of the size of E times the size of S over n to the D. I'll go back to this constant in a moment. Times the L2 norm of f on E complement plus L2 norm of the Fourier transform on S complement. So this constant here gets worse and worse as the size of E times the size of S approaches n to the d. Okay? So this, of course, instantly implies the classical uncertainty principle. Just take a function that's actually supported in E, and whose Fourier transform is actually supported in S, then the right-hand side is 0, which means that the left-hand side is 0. So if you assume that f is not 0, then the assumption must be wrong. And what is the assumption? That the size of E times the size of S is less than n to the d. So the size of E times the size of S must be greater than or equal to n to the d. Okay? So I feel that this really encapsulates the uncertainty principle in a very efficient manner. Okay? And you can probably guess what I'll be talking about for the next 10 or 15 minutes. This result implies the classical uncertainty principle. And we've seen before that the uncertainty principle can be improved in the presence of a restriction estimate. So presumably, one can improve this inequality in the presence of a restriction estimate. And this is what I'm going to do. Any questions up to this point? Because things are starting to get technical, so I want to make sure that. Yeah.
Is this tight in any sense? This Gober and Dunning?
Is this tight? So certainly the range size of E times the size of S being less than n to the d is tight for the usual reasons. To what extent the constant is tight, I'm not sure. I doubt it. Because best constants are very hard to come by. And they're even harder to come by when you're not trying. So the probability of this being the sharp constant is, in the grand scheme of things, is 0. Right? But there are also reasons to believe that it's not off by much. More on that later. All right, so let's go ahead and prove the Gober-Jaman result. This is not quite the proof that they gave, but it doesn't matter. So you take, so one thing that I want to stress is that we are not assuming that E is the support of F. And we're not assuming that S is the support of F hat. E and S are arbitrary sets. Okay? So, and let me make one more point before I go into the proof. Suppose that the Fourier transform is supported in S, but E is an arbitrary set satisfying the size of E times the size of S being less than n to the d. Then on the right-hand side, the L2 norm of F hat disappears. And then what does the inequality say? What this inequality says is that F is concentrated in the complement of any set E, which satisfies the inequality the size of E times the size of S is less than n to the d. And from my point of view, this is the way to think about the uncertainty principle. All right, so we take F and we forcibly localize it to E by multiplying by the indicator function. We take the Fourier transform and we bound it by brute force. So here we're not using any restriction, we're just using a brute force hammer. N to the minus d over 2, size of S to the 1/2 times the L1 norm of F. We're simply dominating it by using the L infinity bound on the Fourier transform. Okay? And so now we bounded this by N to the minus d over 2, size of S to the 1/2, size of E to the 1/2, times the L2 of E norm of F. We are bootstrapping from L1 to L2 by Holder's inequality. Okay? On the other hand, we now estimate the L2 norm of the Fourier transform restricted to E on S complement. Okay? And by the triangle inequality, we bound it from below by the L2 norm of 1E F hat on L2 of Z and D, and we subtract the L2 norm of S. quick question. Am I going to until 3 o'clock or 3:15? It doesn't matter. I just
3 or 5 past 3.
So 3.
Yeah.
okay. No worries. No, because
The next talk is at 3:15.
the words of my PhD advisor always ring in my head. So Sog told me in grad school that a talk doesn't have to be good, but you have to finish on time.
This is also what Vitaly Milman said.
Wait, Millman said this. It must be true. Don't tell Vitaly I said that. Okay, so this is bounded from below by, so we bound the first term from below, the second term from above. And this is why we bootstrap to the L2 norm. So we have L2 norm of E of F times 1 minus n to the minus d over 2, size of S to the 1/2 times size of E to the 1/2. And now you're beginning to see where the constant in the inequality comes from. Okay. And now we're almost ready to drive to the finish line. So by the triangle inequality, the L2 norm of F is bounded by the L2E of E norm of F plus L2 of E complement norm of F. And so L2 of E norm, so this was the point of having this lower bound. We now bound it from above by, well, L2 of E complement is something that we want because that appears on the right-hand side. And here we have L2 of S complement norm of 1 EF hat times 1 over 1 minus the square root of the size of E times the size of S over n to the d. So to finish this proof, we need to unravel this quantity. So we unravel this quantity in the most direct possible way. We write this as F hat minus 1 E complement F hat on L2 of S complement. Okay, times the constant that we inherited from here, plus the L2 norm on E complement. Okay, and once again, there are no tricks here. All of this has to be done this way because we are seeking L2 norm of S complement and L2 of E complement. In other words, what I'm trying to say is that this proof writes itself, but that's not a bad thing. And so now just by the triangle inequality, this is bounded by the L2 of S complement norm of the Fourier transform plus L2 of E complement norm of F times 1 over 1 minus the square root of the size of E times the size of S over n to the d plus the L2 of E complement norm of F. And now we want to unify the constants, and this is why we have this 1 plus 1 over the square root of this quantity, which completes the proof. So in the 3 minutes that remain, I'm going to give you a, first of all, are there any questions about this? Does this make sense? Okay, so let me give you a sort of a quick preview of what is going to happen in the third lectures. So as I said, we have already seen that in the presence of a restriction, non-trivial restriction estimate, we can get a better uncertainty principle. Similarly, we're going to get an improved annihilating pairs estimate in the presence of a restriction estimate. And more precisely, going to prove the following result. This is result from this July. And this is joint work with Philippe Jaman and Azita Mayeli. And it says the following. So if you have a PQ Fourier restriction estimate, if it holds for S and Z and D, with norm CPQ. Now, if P is between 1 and 2, and Q is bigger than or equal to 2, then the L2 norm is once again bounded by a constant times the L2 of E complement norm of F plus L2 of S complement norm of Fourier transform, but the constant is different, and the result is less restrictive. It's the size of E to the 2 minus P over P times S is less than n to the d over CPQ squared. Okay? So, once again, this implies an uncertainty principle. And it implies an uncertainty principle that is slightly better than the one that I stated earlier. Here, instead of 1 over p, you have 2 minus p over p. The only small price that you pay is that n to the d is not divided by the norm of the restriction operator, it's divided by norm squared. So in practical situations, it could happen that having to take the norm squared instead of the norm, if the size of n is not too large, this estimate is occasionally worse. But if CPQ is a fixed size and n is asymptotically large, this estimate is always better. And there will be a corresponding estimate in the case when P and Q are between 1 and 2. Here the numerology is ugly. The reason I'm going to describe this in detail is because there's what I think an interesting wrinkle, because the Hausdorff-Young inequality needs to be used. So in other words, LP methods come into play, not merely Hilbert space methods. And questions like what is the best constant for the Hausdorff-Young inequality in Z and D becomes interesting in this setting. I think I'm going to stop there.